Let's see. Spring break's approaching. Like I think I forgot to mention this the other day. There's no assignment over spring break. I'd be happy to give you one. You want one? Some people had actually said in the midterm feedback, it'd be kind of nice to have more projects, for what it's worth. But I'm not going to give you one. But I might, in fact, if I can, I'll try to remember to put something up that you might want to work on over break if you do want to have some extra time, do more programming. I know I'm getting shaking of heads, but this is completely optional. Be kind of on your own sort of thing, but maybe something to think about so you're not like rusty next week when the next project starts. I could also maybe midway through the spring break, like post the next project, even though we're not going to talk about the stuff until the following Monday. Okay? I apologize about the midterms not being graded yet. We're furiously working on them, but they're kind of long problems to grade. If you think they're long to take, it's just as long to grade, unfortunately. So we will have those. The TAs have promised me by Friday, so before you go on break, we'll have something for you. Yes? You'll get like a PDF version with the, that happened for Comp 11, I hope. It's the same sort of thing. And if you ever want to see the the grades won't be on the hard copy, but you can get the hard copy back if you want on it. It's fine with me, but OK. All right, any other questions before we get going? Today we're talking about a really cool topic. One of my favorite data structures. I say that a lot, I know, I'm a nerd. But this one's kind of cool. This thing called a heap, which my computer decided to die. Hang on. Not my computer, the connection. Let's see. Technical difficulties. When I was at this conference I was at the other day, the technical difficulties were every single presentation I saw on the main stage, there was some technical difficulty. People's batteries dying, other things going on. There we go. OK. I'll try not to touch it too much. Let's see. OK, so anyway, this heaps kind of sounds like what they are, a heap of things. We will get into what they are. And as I said, this past Monday was all set up for this. So we'll get into that. OK? Let's see. What else was I going to say about that? There was something else I was going to say, but of course I forget. OK. Quick little Unix tip of the day. So did you guys like that lab last couple days? Some people were like, no, it was kind of boring. The lab itself, I thought I like it because it shows you a different part of programming, right? You guys got to do like the back end for your website, right? And you guys have a public HTML folder, which now you know about if you didn't before, or you can set one up, and I did that for you for the lab. You can put a web page up there, right? If you want to write a web page, you can put stuff there, and you'll notice that a lot of the links I've given you were some of them are from the Comp 15 webpage. Some are from like my own personal web space on the server. And you can write all sorts of stuff for them. So we'll talk briefly about that. And then, and then it was the front end that we already gave you. OK, so what is this public HTML folder? Well, it's a folder where your username, when you look on www.cs.tufts.edu to your username, it will give you whatever's in that folder. In particular, if you want, what you can do is set up a little index.html file right in that public _HTML folder. And then, unfortunately, it won't be readable by the web server unless you change the permissions, right? And this is how you do it. You say change mode, and it says everybody, that's all, gets to read this file. In other words, it's open to anybody who wants to read it. That's your index.html file. And what that does is it allows the web server to read it, and then whatever your HTML file has in it, it reads it. And what's cool about that is that the back end, you can have it do whatever you want, like do try stuff and all that, which is probably not the first thing you thought of when you thought about what your web page could do. But that's what it can do. OK? All directories in your public HTML folder that you want to put readable files into have to also have the executable permission. That's just another little detail. If you want to know more about that, feel free to ask me about it. But basically, you do all plus read and execute. In other words, you can like run stuff from there. It's just a little detail. OK? And then finally, you can use the programs that are stored on in the public HTML file to actually run, like the C++ one we did. Turns out you have to be a little sneaky about it. If you actually go and look at the code that I used to do it, it's a bit sneaky. But generally, you have lots of like back-end things that you could write the programs in. We don't normally do it in C++, believe it or not, but you can. And it's actually faster if you do it in C++. Does anyone know what famous website was originally built in PHP? Facebook, right? What's that? Twitter might have also been. This is a pretty famous one, but Facebook eventually realized that this is not a very good language. So they changed and went to some other language. I forget, either Python or maybe just straight to C++. I'm not sure. But the back end is, that's where those languages are used. OK? Well, actually, you can also do some stuff in the front end, too. But generally, we don't use C++. But of course, in this class, we do. So that's what I set it up to do. And obviously, this class isn't about web programming. But of course, we have a web programming class here at Tufts. I'm not sure why I'm plugging it, because everybody wants to take it already. But Comp 20, taught by Ming, who is awesome. He teaches Comp 20, and people love it. And it's a great class. And you learn about websites and web design and back-end stuff and all that. So it's a fun class. So if you want, you can take that. All right, questions on your public HTML folder? OK. Let's go back. Remember on Monday, all that work we did on priority queues, right? Remember priority queues, you were able to put things into this data structure. You put a key and an element. And the key is what determines the priority. Generally, it's a number, although it doesn't have to be. Generally, it's a number. And this priority is useful in a priority queue so that you can get out the one with the highest priority. You can either look at the one with the highest priority, or you can remove it. And of course, you can insert in a priority queue as well. And we found out that we had some trade-offs here, right? We implemented it in a couple different ways. We implemented it in the unordered list and then the ordered list. And then we also implemented, well, we kind of mentioned on the board how we would do a binary search tree priority queue. And we got some trade-offs here, right? The unordered list and ordered lists have big trade-offs in that they're it can't be any better than order n to do insert into a ordered list, right? And you can't do any better than order n for min element or remove min in an unordered list. It's just the way the lists are built, right? You don't have enough information to give you back to get better than that asymptotic complexity. It's just the way it goes. And we talked about trade-offs for that. And then the binary search tree, we said, well, look, if you have a balanced binary search tree, yes, it's log n for all of these. And if you have an unbalanced binary search tree, it could be as bad as order n for all of these, although generally it's not. Right? If you insert it into a binary search tree, an ordered list already, then you'd be in trouble for some of these. Right? Could be as bad as order n. But there's trade-offs in there. So as you can maybe guess, there is another data structure, right, called a heap, which actually does things even better. Okay? Heaps will look very familiar to you, but they're interesting in their own right. Okay? And in fact, if you're going to build a priority queue, you'll almost always pick a heap over any of those other choices, as it turns out. Okay? It is a tree-based structure. Okay? You can imagine that's good, because if we're thinking about logarithmic things, the only things we've really seen so far that are logarithmic are either sorted lists or like a tree structure. Okay? They are binary trees in particular. Okay? A heap is a binary tree, but it satisfies a heap property. In other words, there is an invariant for a heap, which is the following. Parents have a higher priority key than any of their children. Let's let that sink in for a second. The parent has a higher priority than any of its children, or its children's children, or grandchildren, or great-grandchildren, or whatever, right? Okay? So by that definition, the node that's at the root has what? Highest priority. Okay, and we care about that, right? So that's why the heap matters. Now, that's not necessarily true in a binary search tree, right? You can always go to the left until you find the one, or the right, depending on how you define it. But for a heap, we're going to have the highest priority at the top. So there are a couple different types of heaps. We will generally be doing min heaps, right? A min heap simply says, hey, the highest priority is the smallest number. A max heap is the exact opposite. the highest priority is the highest number, right? And we do it various ways, but this is the one the min heap is the one you'll see more often. Okay? All right, and let's just look and see if this meets the heap property. Is 5, being the highest priority, a higher priority in both 10 and 8? Yep, and it's higher than 12 and 11, and 10 is higher than 12 and 11, right? Notice it doesn't go 11, 12, and 14 and 13 are backwards, and 10 and 8 are actually backwards as well. 22 and 43 are this way. It doesn't really matter, right? Because the only invariant for this binary tree is that the children have a lower priority than their parent. And it doesn't matter which order they're in on either side. Okay? Can you notice anything else about this tree that's interesting? This might be a little tricky to pick out. About the shape of the tree, maybe? Yeah. It is complete. Yes, and what was the definition of complete again? It's all right if you don't got it. It's all right. Yep.
All the levels are full except the last, which is all the way to the left.
Yeah, all the levels are full except for the last one. So I could not have like a 20 down here, or a 20 here, or a 20 here, right? Because it would not be complete anymore, because the next thing that has to be filled in is the left of this 11. You have to fill that one in next. Okay, that's how these things are going to work out. I guess so. That's another invariant. It has to be complete. But that's what's going on. Okay? Unlike a tree, there are no orderings left and right. Okay? Both of these are heaps. 5, 10, and 12, and 5, 12, and 10. Both heaps because they just meet that heap property, which is that 5 is a higher priority than both 10 or 12. And it doesn't matter which one your children are. Okay? It's impossible to walk through a heap. Well, impossible is a strong word, but it's not easy. If you wanted to, you would have to do something else to walk through a heap in order, right? There's no ordering that you can say, okay, go through this heap in a particular algorithm and get the order out, right? You would have to do some other method, and it wouldn't be efficient. But remember, we don't care about efficiencies with heaps, okay, or with priority queues, except for the minimum one. Okay? All right. Both heaps. So, as we said, heaps are completely filled. The bottom level is not, and so they're complete. The minimum, it has the maximum number of nodes that it can. In other words, the nodes are all filled. We have these as nodes down here, but they're not actually filled. Okay, we'll talk about that in a minute. Internal nodes are to the left of external nodes. In other words, if you've got an external node, or an internal node which is not filled, sorry, I'm lying to you. If you've got a internal node that is filled, it is to the left of any external nodes that are not filled. Okay? Yes? This type of heap has to be binary tree, yes. There are other kinds of heaps that are not, but in general, heaps are binary trees. It's going to make everything a little bit easier for them. Okay? So, yeah, internal so an internal node is just one that's actually filled. Okay, an external one is the one that's not filled. So on a level, the internal ones have to be to the left of the external ones, that's all. Okay? All right. So we get kind of how heaps are set up. It gets a little bit interesting here when we ask ourselves, what's the best way to store a heap? And here's what I want you to do. Talk to your neighbor about this and say, hey, what ways could we store a heap? And you might say there's only one way to store a heap, and it's because it's a binary tree. That might be the answer, but try to think outside the box a little. Okay, take a couple minutes, talk to your neighbor, think about how we might store this binary heap. Okay. Yeah? Ask in a sec. Yeah. Okay, who has some, you have a question, first of all. Yeah.
Can something on the bottom left have a higher priority than the right child on the root?
Can something down here have a higher priority than this one? What do you think?
Yeah.
Why not, right? I mean, it's the only condition is that something the only condition is something going this way is its parents are greater, or in this case, less. So something down here, you could have it less, 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 and this could still be less than this, but it's not doesn't actually like matter. So yeah, so it could be no ordering between the children in that sense. Okay, who has some ideas of how we might? Yeah, another question or comment? Yeah, what's your idea?
So we're thinking something along the lines of an array.
An array.
Weird, but we don't. So a struct would have an array and then a pointer to the next array. And so the next array would be double the size of the previous level's array.
Okay.
In this case, the first level is 1.
Whatever, right? Okay.
In this case, it's
Yeah.
one thing, which is 5. The next one down is 2 things. The next one down is 4.
Oh, I see. So you're gonna have like this is so your first array is gonna be 1, and your second array is gonna be 2 like this, and your third array is gonna be 4 like this, like that, etc. Okay, that's an interesting way of doing it. You're gonna have to keep track of lots of arrays that way, but I can see that. Yeah, okay. All right, that's an idea. What other ideas do we have? Yeah.
You have a binary tree and then an array that has pointers to all the things on the bottom level.
You could have a binary tree, so a node-based one,
Yeah.
like so node, 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 and then what's with the bottom?
Then you can have like an array of things of all pointers to all the leaves.
And okay, so what would the point of having a pointer down here be? So you can get to them quicker?
You can insert things.
Oh, you can insert quicker. Okay, so somewhere up here you've got 2 data structures. You've got the regular one, then you say, hey, this is the next place I can insert, sort of thing.
Yeah.
Okay, that's not a bad idea. Okay, so it's another hybrid kind of approach. Anybody else? Yeah. One array. Okay, how would that work? Okay, so let me see if I get this. What you're saying? Let's see. How many total for this tree up here? How big does my array have to be? You guys know how to figure out how many nodes are in a tree, right? It's actually 2 raised to what? To the height. I like the height. And remember, what was the height from your binary search tree of a no element tree? -1. Whoever said 0 should get that wrong on their homework. And then this, so this is 0, 1, 2, 3. So the height of this tree is actually 3 because you start at the root. Okay. So what is 2 to the 3? That doesn't quite make it though, does it? So okay. So what is it then? 2 to the height. Did somebody else say +1? Yeah. So how about 2 to the height +1? Like that, you mean? So that would be 2 to the 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Almost. Right? -1 maybe? Something like that? Yeah, that's probably how it is. So in this case, we're going to have either 15 or probably 16 because computers are really good at doing 2 raised to something, believe it or not. So let's just make it to the height +1. So 16. 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16. Like that. Okay, and then where do you want to put these things? Okay, so what should go here? 5, and then 10, and then 8. So you're going to read in kind of level order. Okay, and then 12, and then 11, and then 14, and then 13, and then 22, and then 43, and we're left with 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and then the extra. Okay, what does that do for you? You can quickly access any element. Okay, that's fine. It's actually a little better than that. you can quickly access each element, but there's an actual real benefit to this. So I like that idea. OK, so we have that. Notice what I've done here, though. It's almost blasphemous, isn't it? Like I've said, guess what? We're leaving the 0th one blank. That's like all computer scientists everywhere go, no, because zeros counts, right? But we're going to actually do this. We're going to actually put the root at 1, as you'll find out in a minute. So I'm going to cheat on this. Right? I'm going to say that like that, and then just say this like there. Turns out we're not going to lose the benefit of this. We can use it later if we want to. OK? But here's what's going to happen. If you store the tree like this, and I like what you said about it being complete, in that because it's complete, we know where all the pieces are going to go. We know where all the parts are going to go. And yes, we can access them fast, but you haven't seen anything yet. OK? This is me being like super nerd, right? But hold on. OK? Let me write down the actual indexes here. OK? 8 should be here. Notice something about this. If we store this in an array, and you go to any of the array positions, let's pick index 6. The left child of the one at index 6 is what? There isn't one in this case, so let's pick a different one. The left child of the one at index 3 is 2 times that index. So if we go to index 6, then guess what? 14 is the left child of 8. Ooh. The right child is at 2i plus 1. In other words, the left child of position 3, index 3, is 2 times 3 or 6 plus 1, which is 13, because it's index 7. And 13 is the right child of 8. Whoa, that's fast, right? Is there any like walking through this tree to find children? No, right? Now, is it that much more efficient to walk? Well, it's just arithmetic, which is kind of nice. Right? It's kind of nice. The parent, anybody ever see these little symbols before? These little like L sort of things next to the number. You know what that means? Means what? Means floor, which means you round down. So in other words, if we're looking at the parent, right, let's look at the parent of 43, which happens to be at index 9, right? You do 9 divided by 2, but you round down. In other words, 9 divided by 2 is 4.5, but really you round down, which means go to the next integer below, which is 4. So if we look at position 4, it better be the parent of 43, which it is. 12 happens to be at position 4, which is the parent of 43. 12 is also the parent, of course, of 22, which was at 8, because 22 divided by 22 divided by 2 is also 4. Make sense? OK, the math works out. This is why we actually took the 0 and said, forget about the 0 for a minute, so that it makes this math just a little easier. Right? In other words, you would have had to bump this by 1 or 2 here, and this might not have been quite as easy, and it just makes the math a little bit easier. But this is the beautiful thing about heaps, right? You've got this structure here. It's an array. We know how big the array is going to be. It's going to be 2 times the height plus 1. Don't even worry about the minus 1 there, right? And that's how big it is. And if you need to make a bigger array, you make it bigger when you've filled all one level up. You expand it that way. OK? So it's an array-based system instead of a node-based system. This works great for caching. Remember we talked about arrays being great for caching. All the benefits you get from arrays, you get from putting your heap this way. Could you do a binary search tree with an array? What do you think? I don't know, let's do a binary search tree. 6, 20, 10, 4. Could you do that? Could you put your data in a binary search, your binary search tree data doing the same thing? Yeah, Ben?
No, because there is
Okay, there's an implied relationship. That's true. But could I shoehorn this in here maybe? I mean, you probably could. Well, I don't know. What do you think?
You'd have to leave a lot of empty spaces in your array.
This is the problem, right? You'd have to leave a lot of empty space in your array if you wanted to do that. Because remember, it's like whatever the height is, that's how many nodes. 2 to the height plus 1 nodes, right? So in this case, then it's 2. So it's going to be 2 to, it's going to be 8. You need 8 spaces just to hold these 4, right? And if you kept going this way, right, 30 and then 40, all of a sudden now you need 16 positions to hold 1, 2, 3, 4, 5, 6 of them. So you could do it. It's not the end of the world. Okay, you can, by the way, if you did this, you'd still be able to figure out the children that way. Nothing changes. It's still a binary tree. But the reason we use these arrays for heaps is specifically because we've got this nice, perfectly complete tree. And we always know exactly how big it's going to be. And it's not going to grow any bigger than necessary as we add more nodes. Because where does the next node that we add have to go? Left child of 11. So that's going to be here, right? And the next one after that goes to the right child of 11, goes here. And you will fill in here, 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 here. And then you have to make a bigger array. But it's all about being like, you know the structure of it, so it works great for arrays. Yeah, Ben?
Wouldn't it mess up the whole tree structure if you, like, for that array, for that heap, for example, inserted something like 10.5 that's less than all of the elements?
Yeah, if you inserted 1 into this heap, yep, it's going to go right there, and then guess what? You have to do something with it. It's not a heap anymore until you fix it. So we're going to figure that out in a minute. OK, you had another comment?
It was that.
Same thing, yeah. Yeah, the next one goes here, but that's going to be an issue in a minute. OK, you'll see why this is cool in a minute. OK, if you haven't figured it out yet, you'll get all excited like me. OK? All right, so we've got the heap size. We know the heap size is the number of elements in the heap. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's good. You should probably keep an index of where the next available one is, right? The heap size, in this case, it's going to be like the heaps. You're going to put it at heap size plus 1, the next element, right? And again, just forget about the 0 for a minute. We'll use that later when we have to do something with this. OK? All right, so that's how we store a heap. Interesting that we have stored this binary tree in an array. I used to teach where we actually I showed how we could put a binary tree in an array. But this one, the fact that this fits perfectly is I think, a better time to actually put it in there. OK? And easy arithmetic to figure out your children and your parent. OK? Now, why is this? I told you that the other class was all about setting up for heaps. Remember, in a priority queue, because we're going to actually use a heap to make this priority queue. OK, remember, in a priority queue, there's 3 things you want to be able to do, right? You want to be able to get the minimum element. You want to be able to insert an item. And you want to be able to remove the minimum. OK? And by the way, you could also make, if it was a max tree, it would be or max heap, it would be max element and remove max. We're going to focus on the min ones here. OK? So we're going to do min element, insert item, and remove min. All right. If I want min element, think about it for 1 second and tell me what's the asymptotic complexity of min element going to be? Constant? Why is it going to be constant? Isn't it always at position 1? The minimum is going to be at position 1 if this is a heap. So boom, we've immediately said, great, our min element has a order constant, order 1 operation. It's just heap of 1. That's awesome. Okay, remember, we love constant behavior. Yes, Jenny. With the max heap, the whole heap would be kind of flipped upside down. The one at the root would be the 43, and it would still be the one right there. Remember, a max heap just has all the numbers upside down. Like the highest numbers are at the root. OK? All right, so that's order 1 operation for that. OK, so now we have to think about how we might actually go and insert into here. OK? If we're going to insert 9 into this heap, how might we do that? guess what? Your turn to figure this out. Try to figure this out, OK? I'm going to leave this up here. OK, and is this the same one as we had before? Oh, it is. Good. I'll leave that right there. So you've got this to work with, and you've got the array to work with if you want. How would we go about inserting into a binary heap? Okay, in other words, insert 9 with some element. So you don't need to worry about the element. But where does 9 go in this binary heap? Try to figure it out. Okay, take a few minutes to try to figure this out. Because remember, at the end, we have to have a heap again. Right? Once you see it, it'll be awesome. Hey, yeah.
I'm kind of confused as to basically what the invariant is, because could you just insert the 9 at any of the open nodes?
Well, it's up to you, right? But if you want to insert it at, remember it has to be, at the end, we have to have a complete tree, and it has to fit the binary heap property of the fact that the parents all have to be less in this case than the children, right? So if we put 9, I don't know why my pointer's not working anymore. If we put 9 at here, then it doesn't meet the heap property. If we put it here, it doesn't meet the heap property either.
Wait. Oh, because the 11 is bigger than 9.
Yeah.
So it's
Yeah. In fact, everybody here is bigger than 9, so you're going to have to do something with it. Your job is to figure out what that something is. Okay. Hey, Kevin. No cheating.
Sorry about that.
No, that's all right. I want you to figure it out on your own. What are you thinking?
Well, what I was thinking was you move down to see, you move down to find out like which one should be above, and you would find that 9 should be above 10. So
Why couldn't 9 be above 8?
because you have to fill in.
Oh, right. Why couldn't 9 be above 14? Or 13?
Well, don't you have to fill in the one below 11?
Okay, but okay, so you're saying that if these two were filled, you'd try to put it on this side somewhere? Okay, all right. Okay, I like that. Any idea how to code it?
Not.
Okay. All right, all right. Uh-oh, you got quiet when I came up here. I didn't mean for you to stop, but does anybody think they have an idea? I've heard a couple interesting comments. And if you give an idea, you can't have looked at the notes first. Okay. Let's see, who hasn't answered anything lately? Yeah, go ahead.
Well, when you insert it at first, it's going to go into position 10 or the level of 11.
Okay, so hold on. So when you insert it first, it's going to go here.
Yeah.
Okay.
And then what you can do is kind of walk it up the tree.
Can we walk it up the tree?
To its parent.
Compare it to its parent. Okay.
While it's less than the parent, you can switch the position with the parent.
Okay.
11's going to go into position 10.
Okay.
Watch out.
11's going to go into position
8's
there.
Up there.
And then,
you do the same thing again with 10.
okay, and then what?
And then move 10 down to where 11 used to
Okay, and then,
be. And then you're good.
and then you got to compare against this one too, right? You got to keep comparing. Okay, that would work. Anybody else? Yeah.
Does that work? Because wouldn't 11 then be on a lower level than 14 with a higher priority?
11 will be down here. Remember, unless 14 is above 11 in the tree, like in the path back to the root, it doesn't matter. There's no orderings left to right in this case, and either side. Okay, yeah. Nathan.
One way to do it that would work from an array perspective would be to start at the far end of the array.
Here,
Yes,
yeah.
and then walk backwards, shifting the elements over as you go until you find an element that is less than it, and then insert it directly after that one.
So you're saying move the elements this way until you, that I am going to guess that you're not going to have a problem with that, because there might be,
It's going to work in every case.
it's not going to work in every case, because you might have a 14, 13 not be able to be next to each other one level up, right?
Yeah.
It might be like if you move to the the 14 up here, it's greater than 30, you're in trouble or whatever, right? So that's not a bad idea, but I think you might run into trouble. You might be able to figure out a little better way. Yeah? You have a question or a comment? Yeah. Oh, that was the issue. Yeah, Zoe.
In the array, can't you use the like I divided by 2?
Sure, you can use the I divided by 2. If you're at 10, I divided by 2 floor gives you 5. So that means whatever is at position 5 would be the parent of this guy. 11, and that is the, if we put 10, if we put a number here, then this one's the parent of it. Yep, okay, I like that. Any other ideas? Did anybody think maybe, what if we just put it here and then kind of checked the children and see if we could put it on either side? Anybody try that out? Maybe? I don't know. I've heard that idea before. Like you try to put 9 here and you say, okay, well, it's greater than 5, so it's got to be here, and it's less than 10, but greater than 8, so it can go in here. So 8 has to maybe, whatever, maybe. I don't know. Yeah.
That would be a little weird though, because in the end we know we're going to have an extra number. So why wouldn't we start from there?
Yeah, I like that too. We know that after we get done with this, whatever this heap looks like, the answer is going to be the next. It's going to be filled, and then this one's going to be filled. So we know that. So you're right. If you tried to stick it down here somewhere, you'd end up with something over there, and then you'd be in trouble, right? So okay, I like that. All right. So as it turns out, that was the right answer. Very good. Okay. Did anybody else come up with that idea? Yeah, a couple people. Yeah. This actually is exactly how you do it. Okay. What you do is you insert the element at heap size plus 1. And we said that this was a heap size of 9, so you insert it at heap size 10. So let's actually do that. And then we'll do a little bit of the math to figure out. We'll do the mathy part and then see if it works out. I'll animate it for you in a minute. OK, so we put the element at heap size plus 1. OK? And then, that's another reason why this is cool. We have this feature called a bubble up. It's also called an up heap, but I like bubble up better. It sounds cooler. Right? We're going to bubble up or upheap the element. In other words, you compare it to its parent, right? And we can do that. In fact, I will draw this just so that we can see what's going on. I'll do it in both the array and on here. OK, of course, I forgot what it was. So it's easy to get back from this, right? 5, 10, 8. Notice I'm always going left to right here as we do this. 5, 10, 8, 12, 11, 14, 13. 12, 11, 14, 13. OK, 22, 43. 22, 43. And then we're just going to put 9 right there, like that. OK, so that's now what we've started with, right? And we're going to say, OK, compare to its parent. In this case, it's going to be 11. How do we know it's 11? Because 10 divided by 2, floor, is 5, and that's this one. OK, who's got to be higher in the heap, 9 or 11? 9. So what we do is we just swap them. OK, 9 and 11 get swapped like that. And we can do that graphically over here. 9 and 11. Do the same thing. OK, now we've got it. We've just put it in position 5. So 5 divided by 2 floor gives you what? 2. So you'd better check against 2, which is 10. And notice it is the parent of 10. Who should be higher in the heap? 9 should be higher. So we're going to swap 9 with 10, like that. OK, and then we have one more. And we have to do it over here graphically. All right. And we've got 9 and 10. And then we have to do one more comparison, which is between where it is now. 2 divided by 1, floor, is just 1. So we compare 5 to 9. Who should be higher? 5 should be higher. So therefore, we're done. We don't do any swapping. And once you find a place where you don't need to swap, you can stop. OK? And do we have a heap now? We do. It meets both criteria that we have. It meets the invariant that at any node, all of its children on both sides are lower priority. And it meets the condition that it's a full or a complete tree. OK? Pretty easy. That bubble up is the part that you have to kind of consider. OK? All right. Let me show you the little animation we've got. This is the same animation we've seen before. Just to do it again, if we, let's see, let me move this up here, move controls up here, and yeah, we can do it fast to start out with. OK, let's just insert these in our regular order so it goes in the way we want. 5 and 9 and 8. I'll actually make it really fast. 5 and 9 and 8 and 12 and 10 and 14, 13, 22, 14, 13, 22, and 43 and 11. And then we insert 9, and I'm going to slow it down a little to see what happens. Did I miss one? Oh, I put it in there already. Let's insert something else. How about we insert, oh, let me make this go down. Hang on. Whoops. OK, we'll insert 7. We'll insert 7. Where is 7 going to go? Right here. It has to go there. It can't go anywhere else. And what's nice is it's going to go there, and it's going to be the last element, heap size plus 1. That's where it's going to go. So it's really fast to do this, right? So 7 is going to go in there, and then once it does that, right, it's going to be compared to the 10, compared to the 9, compared to the 5, and we're good. All right. What about 1? What if we inserted 1 in here? Right? 1 is going to go over here, compare with 14, compare with 8, compare with 5, and it gets swapped. And we're back to a heap. OK? See how that works now? Pretty straightforward. This bubble up or up heap operation is pretty easy to do. What's the asymptotic complexity? Think about it. Yeah? Why log n? You're only going up the tree, the height, right? And remember, the height of a binary tree is, well, basically the logarithm of 2 to the logarithm of 2 raised to the height divided by, so it's really it is the height, basically. So it's the logarithm of the number of nodes, right? So so it's definitely logarithmic going up there. So that's kind of cool. We definitely get a logarithmic behavior here. Insert and then bubble up. And by the way, because we're using an array, it's going to be super fast. It's neat. OK. All right. So that's how you do bubble up. OK. You can definitely go and look at more of these visualizations later if you want. OK. Oh, here it is again. Same thing. Swap, swap, swap. And we're done. OK. Worst case, log n. Average. Now, this is going to be interesting. Average complexity is actually constant. Now, I'm not going to prove that to you. You can go look at this fancy schmancy paper here where it talks about that. I went and read it once, and my head kind of started spinning a little, right? Because it is a little bit in depth. But they approved, and it made it into a conference or whatever. So ostensibly, people who know what they're talking about reviewed it and said, looks good. That you can, on average, the complexity is actually constant, right? Because, and if you think about it, how many times are you going to go all the way up to the top of the tree, right, or the heap? Not that often, right? Only if it happens to be the highest priority you're inserting. It's the only time it would ever go all the way up. So kind of on average, you can think, OK, it's not going to go all the way up, so it's going to go some portion of the way up. So that's kind of an intuitive way of thinking about it. OK? Very cool. All right. Of course, we have to do this. Don't get flashbacks from homework 4. Remove min. Okay. Take 5 minutes and think about this one. Okay. It's backwards. 7, 9, 8, 12, 10. 9, 8, 12, 10. 11. Okay, what do you guys think? Who has an idea? Colleen, what do you think?
So you take the last element.
Take the last element, which is 13. You didn't peek at this, did you?
No.
Okay. Last element, which is 13, yeah.
Yeah, 13, and you replace it with the root. You're going to take the root off, obviously.
Okay, so the root is going to be removed because we're gonna not have it. So 13 is going to be here, and then what?
You compare it to its children.
Compare it to its children, okay.
And you compare it to the one that's smaller of the two children. So compare the two children first, and then you compare the root to the smaller child.
Okay, okay, 8,
And then you bubble down or heap down, whatever. So
Bubble down, okay, all right.
then you would swap 8 with 13, and then you would compare it to its two. So then 8 would be at the root, and 13 would be where 8 is.
Uh-huh.
And then you compare it to the children again, then you have to swap it with 11.
And swap it with 11, okay.
And then
Okay. Does that work for, is there a case where you could actually go the wrong way and then have something down here have to be the one that you wanted to move up there?
Well, wouldn't it always have to be one of the two children that would have to be at the root?
Why does it have to be one of the two children?
Because, yeah.
Well, yeah, I want you to think through this, right? Think it through. You're right, but why is that case? Yeah.
So for either of the left or right subtrees,
Yeah.
the smallest has to be at the top because of the heap property.
For each of the subtrees, you definitely have to have the smallest of the subtree side at the least of that. Yeah. So the least of this subtree has to be this one, and the least of this subtree has to be this one, which is where you were getting at, right? So the idea is then you definitely only have to compare against two things, right? Yeah. You can't have it such that there's something else that's you could have these ones all being less than this one, couldn't you? But you can't have this one being greater than, or it's this one and then all the other ones being less. It just doesn't make any sense, right? It would not meet the heap property anymore. Okay? Interesting. Okay, so I like that. Did anybody have a different way of doing it? Because there are other solutions possibly. Yeah, Ben.
I'm not sure if this would, like, it seems like this might work with the array structure. So,
Okay.
so take the root and remove it.
Okay, so root's gone. Yep.
Then compare all, like this would happen over and over again for each level. Compare the items in that level to find the smallest one.
So basically, take this one and compare the levels. Now, when we did it before, you definitely knew something about these two, right? Well, have you put the 13 in anywhere yet, or no? Oh, okay. You haven't done that. Okay, so you're comparing. So do we have to do 3 comparisons then?
Well,
Or rather, compare 3 things?
comparison for each level.
Oh, okay. So all right. So let me get this. What are we putting in here? Oh, the 5 is going away. Okay. So we're comparing. So.
This would be super inefficient.
Well, it might be inefficient, but it's not bad to talk about it. But I see what you're trying to do. You're trying to basically find the minimum on these, like, of these ones, right? And then what would you do? Go down and down and then eventually, and then where would you put the yeah, I mean you might end up, in this case you would end up bumping this one up to here, and then like what would happen with these ones? One would have to swap over, and then you'd be a problem because one of these would be gone, and you got to have it down here, the one that's good. This one's going to be the one that's going to be gone. Yeah, so you have to be a little careful. You might be able to get around it, but yeah, not the most efficient way to do it. Yeah, Nathan.
I think you could do it recursively by removing the top one, by removing the top one, finding the lower of its two children.
Moving the top one, finding the lower of its two children, okay.
Putting that one in its, copying that one into its place and then recursively removing that.
And then doing this one?
Yeah.
Recursively, okay, but then again, you'll end up with the two here. One of these will get removed, and then you'll have a non-complete tree, right? Which you could probably fix by basically moving this one over here or something weird like that, but then you might have a problem of bumping back up. So as it turns out, Kalina's answer was actually right. Okay, the key here is go to the node you know has to change and do something with it, right? That was what we did for the insert, right? We said that if we were inserting into this heap, we'd have to put it here because that's the next one we got to fill. Kalina's solution is, look, take the node from here because that's the one that has to be empty next time. Throw this one at the top, and then it is literally called bubble down or down heap, right? And you're going to basically compare it to its smaller and swap it with its smaller child, and then do another comparison with its smaller child. And at the end, you will have another heap here that's fine. So let's do that on here, right? OK, so we take the 13. The 5 is going to go away. Whether you return it or not depends on what you've actually done. OK, so that's going to do it. And then let's get rid of the 13 because that's the one that we're going to use the 13 because our heap has to look like that in the end. It has to be that form at the end. Put the 13 here and then start comparing. Now you do have to do two comparisons, right? You have to compare which one of the two children is the smallest. And by the way, when you do this in lab, when we get back, you'll have to implement this. And it's a little tricky because there's special cases, as you can imagine. Well, not really special cases, but you have to care about whether there's one child or two, and then what do you do? And the comparisons get a little bit ugly, but it's not too bad. Compare the one that's smaller you're going to swap with, right? So the 8 is going to be here. And we already talked about the fact that now that's guaranteed to be the next minimum. So 13 would be here. Let's swap these here. And we can do it by checking the children, left child, right child, etc. Right? Oh, did I do it backwards? Let's see. The 13 was going to go here. And then it's going to swap with, did I not put the 8 in this one? Oh no, I have a different wrong tree. Well, we'll do it on. We'll assume that works. 8, or that it's correct. 13 is now going to be switched with its smallest child, 13, and now do we have a proper heap? We do. Okay. Now we have a proper heap again. Okay. All right. So that's good. This is the actual algorithm. All right. Retain a complete tree. So replace the root with the last element. Bubble it down, which is compare the root with its children, and if in the correct order, you're done. If not, swap with the smallest child, and then repeat step 2. So yes, you can do it recursively, by the way. OK, you can definitely do this recursively. All right, and then be careful to check whether the children exist. That was what I was talking about before. If the left, by the way, if the left child exists, right, you know the right child has to exist. Because, did I say it wrong? If the right one exists, thank you. If the right one exists, then the left one has to exist because it has to be a complete tree, and there's no way to have a right child and not a left child. Okay? All right, so that's the algorithm. I kind of showed it to you there. Move the 5, 13 goes up there, bubble down, bubble down, bubble down, and we're done. Okay? I don't think we need to do the animation online again for that, but it's the same idea every time. Okay? You can practice these a lot too. All right. So those are the, and by the way, what's the asymptotic complexity of this? What do you think? Yeah? Yeah, again, it's going to be log n. In this one, it's going to be log n because it could bubble all the way down to the bottom. What if we, and in fact, it's going to be more often log n because where are you taking the one that you're putting at the root? From the bottom, right? So it's going to not invariably, more often than not, have to bubble down at least a couple levels because it was already pretty big to begin with, in general. Okay, not always, but that's it. So this is definitely a logarithmic one. This is not like somehow average of 1. It's just logarithmic. Okay? All right. All right, so there's your heap. 3 functions for the heap. Now, I want to talk about what the best way to actually build a heap from scratch. In other words, I have a bunch of numbers, and they're in some sort of random order. And I want to build a heap from them. OK? We have time. One last time. Try to do this on your own. Tell me how you would do this. Could be really easy. Tell me how you do this. And then we'll actually build this heap. Yeah. I mean, turn these numbers into a heap. Right? Because right now they're just kind of random numbers, right? And if you put them, like, if you just tried to, well, I mean, you could make a heap from them pretty easily, but it might not be the most efficient way. We'll talk about it. Did you say first you sort them?
Yes.
Okay, that's one way to do it. Is that a heap if they're in order?
Well, yes. Because each one's very short.
Yeah, that would work. Yeah, you could do that. I would say it's not the most efficient way. Yeah. Okay, the noise has calmed. Who thinks they have an idea? Nate, go ahead, give us your idea first. What did you say you wanted to do?
You just sort it.
You could sort it. So somehow we're going to sort this. So basically, throw these into an array and do an insertion sort or something, and you're going to do that, or do an insertion sort as you go, and that would become a heap. Sure, that would be n squared, or maybe some other type of sorting behavior. So yeah, you could do that. There's probably a better way. Probably a better way. Yeah. You think?
If you want to build it top down, you can do it in log n time. But if you built it from bottom up, you can do it in linear time.
Hang on. Hold on. If you build it from top down, what do you mean?
So basically, you keep inserting over and over.
OK, did everybody come up with that solution where you just insert 14 into a heap, and then there's a heap, right? If we insert 14 into a heap, there's your heap, right? And if we insert 9 into a heap, into this heap, right? Remember what we do with insert. We put it at the next one, and then we bubble it up, right? Like that. And then 9 and 14. And then we insert the next one into the heap, and that would be 13. And that would go there, and it doesn't need to be bubbled up. And then we insert 43, and that doesn't need to be bubbled up. Then we insert 10. And 10 does need to be bubbled up, so it becomes 10, 14. You see how that works? That would be one way to do it. OK, now, you're claiming that that's inefficient. Why? What's the asymptotic complexity of each one of those inserts? Each insert's log n. Remember, we did say on average insert's going to be not log n, but constant. But yeah, I'll buy that. OK, so now you're saying there's some other. Sorry, Ben, you had a question? No, OK. So you're saying there's some other way. So now you're saying that was building it from the top down. OK, how do you build it from the bottom up?
So you just put the array
OK, hold on. You put the array as is into the heap. In other words, you put the array into the. You put these numbers into an array as they are. Is that what you're saying? OK, so it would be 14, 9, 13, 43. So let's do that. This is going to be 14, 9, 13, 43, 10, 8, 11, 22, and 12, like that. OK, and let's just do this one out here. It's going to be 14 and 9 and 13. and 43 and 10, whoops, 10 and 8 and 11, 22 and 12. 11, 22 and 12. Okay, so now we've got we've got the array. It's not really a heap yet, but it's an array. Okay, and then what?
So basically 8, 11, 22, and 12 are already basically heaps of size 1 on their own. So what we can do is basically just start our problem by iterating from the end of the array, going incrementing down. So we can start at 10.
Start at 10, okay.
43.
Start at which one?
43.
Start at 43, not 10, okay. Because why you're saying that 12, 22, 11, 8, 10 and are all already heaps. Is that what you're kind of saying? Okay. And then what do we do at 43?
So 43 we can do basically heapify each node before.
You've read this before, haven't you?
We covered it in concept 6.
Whoa, that's cheating if you're telling me you've done it before. All right. Everybody following that? Somebody who knows the answer is giving you the answer. Okay? All right, hold on. So when you said heapify, I said you've seen this before. Heapify being bubble down in this case. Okay, it's another thing to call this. Okay, so we do have the answer we would probably be given. Hold pause on that. Did anybody else come up with a different answer? Like something that they thought maybe that did. First of all, did you come up with the answer where you insert into the heap like we talked about? Okay, all right, keep going now. What are you trying to do each time?
So you basically heapify, so you look at the 43 and you make sure that it falls right there.
You down heap 43, right? Okay, so which one gets replaced with it? The 12, because it's the minimum child. Remember, we're down heaping. So 12 goes here and 43 goes there. Okay, let me swap it here. 12 and 43. 12 and 43. Okay, and then what do you do with, then what do you do? Then you heapify 13, because we'll get back to 12 if it needs to be changed later when we get up to here, right? So you're going backwards through this, and you're going to heapify 13, down heap 13, right? So what happens here? 13 and 8, 8 and 13, and that's good. Okay, then I better change it. 8 and 13, and we're just doing the parent thing again, right? Zoe, I'll be with you in a minute. Okay, 13. And then now we've done the 8 one. Okay, what's coming next? 9. So 9, does 9 need to change with any of its children? Nope, it's fine because they're both already greater. And then last thing we do? Heapify 14, so which one gets changed? It switches with the 8, like this, like that. And is that now a heap? Oh, did we do it wrong? Yeah, we missed 11 and 14, so what happened?
Part of it is like once you see, so when you're at the root, basically heapifying down as much as will happen.
Yeah, you keep heapifying down, right? Don't forget to do that, right? When we did this one, we forgot to do 14. We did 14, we go, oh, we're done. Not quite, right? 14 has to be heapified all the way down, 11 and 14. And now is it a heap? Yeah, now, did we do everybody else correct? Yeah, we did everybody else correctly. So 8, 9, 11, 12, 10, 13, 14, 22, 43. OK. All right. Zoe, you had a comment or question? Good question. How did you know which one to start with? And that is a good question. Yep. OK. I'm not going to give the person who knows the answer the benefit of answering that question. Yeah, what do you think?
So could we do the same comparison we made before to the parent? So we saw that the very beginning, if I remember correctly, 43 and 12 were in the first location. So we said, well, is 12, because we started at the end, is 12 need to be swapped with its parent? In which case the answer is
But how did you find 12 to begin with?
it was the last one in the
The last one that what?
that was in the array.
That has any children. That's how you find it out. So you go to the one that has last children. Now, guess what? Turns out that the last one that has any children is at what position? Any ideas? Heap size here is 9. Okay, which one of these ones is the last one with no children? Still 12, right? So 12 is going to be which position? 12 is going to be at position 4. Heap size divided by 2, maybe? Heap size divided by 2 will give you the first one you have to care about, which happens to be the first one that has no children. All right, it works out perfectly that way. Okay? So we did talk about this. We could insert that n log n. Better way is to insert all the elements starting from the lowest completely filled level at the first node with children, which is nice, and that happens to be at position n divided by 2, technically floor of n divided by 2. Down heap each element, completely down heap each element. Okay? And so inserting into the elements is n, right? And down heaping each one is going to be n to do the whole tree, as it turns out. Okay? Yeah? No. You're actually starting with n divided by 2 in the array. So in other words, let's look at this one again. Pretend this was not heaped, not already. The first one we care about is this one. Okay? As we said earlier, all the other ones are actually already their own little heaps, which is fine. That's kind of one way you could think about it. Or you could just say, look, the only one that we're going to care about starting with is this. We only need to do this one, this one, this one, and this one, because it will eventually pick up anything lower than that. You don't need to. Nothing's going to happen if we try to start at 43. There are no children, so nothing's going to change. Right, but we didn't start with that. We started with this one, and it swapped with 43. So we started with this one. Let's actually, I think it's right here. I'll show you again. Okay, here we go. All right. This is what we start with this one. If we started with this one, would we do any down heaping? There's nowhere to down heap, right? Down heap, down heap, down heap, down heap. There's nothing to do. So don't bother. You know there's nothing to do for those guys. So we don't need to start with those. Turns out you can always start with the heap size divided by 2, which is this one, right, in this case. Okay? If we added another one, it would be this one, right? Because now it would be a heap size of 10. 10 divided by 2 is 5. 0, 1, 2, 3, 1, 2, 3, 4, 5. So it's always going to be the one that has children that's the farthest to the left on the complete level, or the left below. Yeah? The floor, yeah. Yeah, it's implied in this case, but yes, the floor, yes. Okay, all right, so anyway, so this we'll do it right up here again so you can see it again. We kind of went a little bit fast on the board. Okay, all right, so what we're going to do is we're going to start with this one and then down heap 43. Boom, that swaps with 12. Okay, and 43 and 12 swap. All right, then we're going to go up to this one, and we're going to walk backwards. This is going to be a for loop going backwards from n divided by 2 to 0. All right. And now I equals 3, which is here, and we're going to check 13 versus 8 and 11, and it ends up being 13 and 8 swap, because 8 is the smallest child of 13. Okay. Then we're going to check I equals 2, which is this one. 9 is already greater than 12 and 10, right? And then we're going to go to 1, and then 14 has to swap with 8, but then also it has to swap here because we have to down heap completely. Okay? And we're done. Turns out that's faster than doing it, than inserting each time. Yes, Gabrielle?
Would you want to start that off with like the last parent, or like the node that's farthest to the left on the last full level?
Yeah, it's n divided by 2. It's the number of nodes, or it's heap size rather, divided by 2.
So like if there was a number after 4, well.
Let's say there was one here. What's the heap size going to be? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So heap size would be 10, right? Heap size divided by 2 is 5. 1, 2, 3, 4, 5. We start with this one, right? So you always start with the heap size divided by 2. It's actually a really easy loop once you do it. And if you already have down heap, it's a super duper easy loop, right? It's a for loop. For I is heap size divided by 2. I is greater than 0, right? And then that will walk through all of them, and then down heap inside the body of the loop, and that's it. Yeah, good, great. All right, so that is that. Any questions on heaps? Yes, John?
So the idea that it's a binary tree is really just for us.
The idea that it's a binary tree is for us. Yeah, that's pretty much true of any tree structure, right? Like, I mean, it's not really like under the covers. I suppose the node-based ones, like there really is a node kind of structure to it. You're right. We're implying this structure from the array. Yeah, so it's a model. We're modeling this structure inside the array, yes. Yep, good. Yeah?
And then, so in this case, we had to take 43 and bring it down, or not 43, the topmost number, bring it down twice, 14.
Yeah, you'd have to bring, well, because remember it was down heaping. It was down heaping from up here, and down heaping 14 is a two like jump thing. You have to check with this one, then you keep down heaping it, and it's going to swap with that one.
And so
Yeah.
to continue to keep down heaping it, does that mean that in down heap it calls itself again?
Sure, down heap can be recursive. Yeah, probably should be. Yep, or you could do it using a loop. Okay. Any other questions on heaps? Yes. Yeah, what's the time complexity of this one? Linear, yeah. It's actually, you can get order n to actually do it. It's actually 2n because you kind of have to insert them all first and then go through them again. But it's actually linear to do this, which is very cool, right? Okay, you can do this. Very cool. Now, how would we sort using this heap? Like, how would we now sort? This is exactly what we talked about this right at the end of class, I believe, the other day. Can we make a sort out of this? Like, how do we get 8, 9, 10, 11, 12, 13, 14, 22, 43 out of this? Yeah? Keep removing them in. You remove them in, and then you heapify it. Well, you remove them in by bringing the 43 up here, down heaping it, right? And then you'd remove them in, which would be 9 now, and you'd down heap the 22. And then you'd remove min, which would be 10, because that would bubble up to here. And you do that. This is called a heap sort. And it's your first real sorting out, well, second sort after the insertion sort, I suppose. OK? Talk more about heap sort. You'll actually do a heap sort in lab, as it turns out. Yeah?
Why would you do this instead of just inserting all the things if it's the same complexity?
It is better complexity, actually.
Aren't they both?
No, they're n squared to do the complexity for insertion sort, for all of them. N for each element, and then for every element again, n squared. N, so it's n squared. In this case, it's just a total of n to insert, log n to get it out, and log n total, as it turns out. Yeah. So, OK, any other questions? All right, see you guys after break. Have a good spring break.